Okay, sometimes the LDAR doesn't work. I don't know why. All right, lab 12, Tuesday. Tuesday, right? Yeah, I've lost track of time. All this is ordinary differential equations. And I think what served me well in the previous lab was this. Whenever you see differential equation problem, there's so many applications of this. It's like, I'm not even joking. Engineering professors love differential equations. You can use them for, well, I'll just show you. I mean, you can graph like these like beautiful butterfly effects in 3D space. You can track air currents. You can do all sorts of crazy stuff. Like what a differential equation is, just as a refresher, is like kind of you have like y plus y prime plus like y double prime equals 0. It's like you have some quantity plus its derivatives, and like that is your equation. It's as opposed to like, oh, you have y equals x, and that's just that's a regular equation. But if we're doing differential equations, we'll need to use like some sort of method to solve it. And it's a little bit tedious at times. So what MATLAB does is, just tell it what the function is and then use a function called ODE45. There's other ODE solvers out there, but this is the one we're going to use. This is going to solve us the differential equation for us and spare us all that extra hand calculation work and break our wrists. So the parts I want to go over are this. So the one thing we'll need to have is obviously the differential equations. And then as kind of an aside to that, like some parameters, like gravity, like just how we're going to set up the problem. Because our differential equation might have constants, and then we'll need to plug those in. The other thing we'll need is initial conditions. Initial conditions are like our start point. If we have like a radioactive decay problem, we have some amount of bacteria and then they're dying off in a petri dish, or they're growing in a petri dish. How does that change over time? Well, first of all, we need to know how much bacteria we start with. If we have like, over carbon dating, how much carbon-14 do we start with? And then how much has it decay over time? That's the differential equation that's going to tell us. Initial condition, and then finally, we're going to need the ODE solver itself. So ODE, one more thing actually, time span. Time span. How long are we going to look at this decay or growth or air current circling problem? That's our time span. Lastly, we're going to plug it all into ODE45. ODE45 is going to take, so it's the differential. Let me remember the syntax for this. It's like you'll have at function. That's some function we defined. Typically, what we're doing here is we're making an anonymous function and just using one line, have that be your differential equation, which you might guess might produce a really, really ugly line. Break it apart if you need, and it like stretches off the screen. You'll see that in part 2, problem 2. I mean, you'll do that. You'll do like, I think it's a time span next. So like they'll write T span and then followed by like the initial conditions, ICs. I think there's some other stuff you can define later on as well for ODE45. ODE45, if you need the syntax for that, just go on MATLAB's either the online documentation or just type in help or online. Okay, this is a breakdown of how to solve a differential equation. This applies to every single problem we're going to see here, and probably a lot of differential equation problems you'll see in the future, because they already give you the equations. Like they've done the hard part for you. So first one, let's see if we can, play a little bit of spot the part. Where is our differential equation? That's going to be defined here, and also here in matrix format. Well, vector format, I should say. Okay, initial condition, where do we have those? Okay, we have 5 initial conditions. I'm going to just label these like 2 and 1. Initial conditions. The Lorenz attractor is just a 3D plot with like 2 of these like binary star systems. And then you have an astronaut and you start cycling around like this. You make this like beautiful butterfly / figure 8 configuration. This has to do with like air currents in the atmosphere kind of thing, but like imagine they're binary stars. What was I? Okay, we have the initial conditions. You put your astronaut at like various points in this graph, and let's see. So this part's just plotting. Where do we define a time span? I guess. Time span. I guess it doesn't tell us what the time span is. Maybe it's oh, here it is. Very small. Here's the parameters, by the way, for the Lorentz attractor problem. You'll see us like, oh, sigma, we have beta, we have, what else? No, sigma, rho, and beta. So those are just numbers we define for the purposes of this problem. You won't see those again. Go here, and we'll plug those in. Now, the plot 3, this is the syntax for a 3D plot. So you have like an x, y, and a z-axis. And hold on just tells you put every single one of these initial conditions on the same problem, on the same graph. All 5 astronauts are going to be flying around in space, trying not to hit each other, like so. And then there's going to be, check the solution for this. Like it'll tell you how to make a PNG file using MATLAB. Okay, OD45, motion of double pendulum. Okay, all of that was problem 1. I am going to get rid of this part for problem 1 so we can go on to the next page. The thing with these differential equation problems is that sometimes they produce some really beautiful graphs. Number 1 especially. I'll trim this part off as well, so we're not blocking too much. Okay, Lorentz attractor, invented by a guy named Lorentz. Who knew? Double pendulum. I'm gonna zoom in on this so you guys can see. It looks scary. The solution has it, but if you wanted to code this yourself, what I would recommend is splitting this up. Like you will make mistakes if you try to code all of this in one line, or it'll be very, very painful to do. Like my advice is this: sine, cosine, sine, cosine, sine, sine, cosine. All of these can be just their own separate line. Like I don't know, sine, cosine. This one has a beta. This one has a sine. So maybe like I don't know, S1, S2, S3, stuff like that. Pull it out and then insert these into the equation after you've created all these intermediate variables, just to make life easier. That's not like a differential equation thing. That's just a coding thing. So whenever you're being asked to create something huge like this, break it up. Unless you can avoid it, which is like very rare, I think. You want to make sure that you can read your code. This is not very readable. It's complicated because the problem is complicated. Like you plot this out, you'll make a video out of this. I mean, just check the solution on that. And it becomes very, very chaotic. Like it swings back and forth and creates all these like it's chaotic, but we can predict the motion just because we know the initial conditions. All right, parameters. This is 1. This is still a 1. There's a lot of things we need to tell MATLAB before we set this up, because this has like a bunch of stuff that, oh, how long is the rod? How massive is the rod? What angle are they at? Oh, sorry, these are initial conditions. My mistake. These are 3. This is where we start. Like, do we like pull this one out to like 90 degrees and then start swinging it? Do we pull both of them? That kind of thing. Where do we start the rod? And where is the, sorry, my number doing, this should be 2. Initial condition, time span. Okay, where's the time span? Time span of 0 to 20 seconds. I think they're using a pretty similar time span for all of these. Specify. Okay, and then specify the outputs of OD45 should be every 1/30th seconds. That's like one of the additional options, isn't it? Wait, Nikolai, I might need your help on this actually.
Sorry, what was the question?
Oh, so I was just wondering, specifying that the outputs of OD45 should be every 1/30th seconds. Is that like, do you specify like the step in like an additional argument?
And no, you can define your T-span array to be from the initial time to the final time in steps that you want the answer to be in.
So would you plug it in as a vector? Like you have your ODE45. You have like your function, you have your, here's your time span. My memory was that you plugged in the initial and the final, right? How do you specify like the 1/30th seconds part?
You can also plug in a vector of time. So if you want it every second or every 2 seconds, you would do this.
Oh, like so?
Or every 1/30th, it would be like this.
Gotcha. Okay. Okay. Makes sense.
If I'm not mistaken. But
thanks, Nikolai.
I think that was it.
Always. Oh. Whoops. Okay, I need to read. Yeah, I need to read more. All right. There we go. Yeah, it says it right there. Define a function.
Oh, it's in the lab file. Yeah.
It says in the very next one. Okay, well, that's 3. ODE45 is just, well, it tells you to use ODE45. Okay, that's question 2. Question 3. We have differential equation. Check. Simplicity, mu equals 1. That's kind of the parameter that goes to 1. Initial condition. Let's go to the next page. This one you'll use like 2 different methods of doing the same thing. Instead of like having like, oh, you have a, wait, is this ODE45 even? I think for this one, they're doing something a little bit different. Instead of using the solver, they're doing, okay, it's like ODE45, but it's a different solver. You've seen one of these before, the Euler's method, where like, okay, you have like your y at like time equals 1, and then like time equals 2, you have like well, n plus 1, I should say. Okay, I should write these as n's actually. Y of n, this is known. You know where you're standing, but where are you going? Y n plus 1. What is that? And then this will tell you where that is. Now, there's 2 different ways of doing it. One's called Euler, one's called RK4. There's just 2 different ways of doing the same problem. The big picture is they're doing what ODE45 is kind of doing. Some of these are more accurate than others. And you'll code each of these. Initial conditions as usual, time step. What I want to impress upon you guys is that all of these are just super convoluted ways of doing the same thing. You'll have some, like step 4, if we wanted, we can replace that with just any ODE solver. You'll have differential equation, where you're starting with, how much time you're doing it over, and then finally you'll do the ODE solver. Question 4. Okay, here you're doing all 3 of them. Everyone's here. ODE45, Euler, and RK4. You look at all this. All of this is just the parameters for the problem. All these go into 1. All of these are the initial conditions. Where does the sun, the planet, the moon start? And the rest of it's just specifying the time span. Okay. A lot of this, I assume, you're not very motivated to actually look at just because you already have the solutions in front of you. But my advice is this. If, like, try going through this yourself and, like, just kind of, if you're not confident with, like, going through the entire thing, just create the basic structure, set up, oh, what are my initial conditions? What's my differential equation? What's my initial condition? To find the time span, and see how you would set it up. Then go into the solutions, like compare your logic with theirs. That's how I would approach it, just so that you have a framework for how this kind of problem is set up, because you will use differential equations in the future. Chances are. I'm not sure what your guys' majors are, but at least in engineering, these people love to use these a lot, even if you don't expect to. I will stop for questions. Keep this basic structure up. Okay, how are people doing? Vibe check. No 10s requirement because there's only one session. Yeah. Don't hear questions. I'm going to stop share then. And stop the recording.